When we hear the word tsunami, our minds drift to Earth's oceans, vast, restless, and alive with motion. We imagine towering waves rising from the deep, sweeping across coastlines with unimaginable force. Tsunamis are symbols of nature's raw power, reminders of the delicate line between beauty and destruction. But what if these waves are not limited to Earth? What if the universe itself, a boundless sea of stars, planets, and forces, hosts its own version of tsunamis? In this film, we will travel beyond the familiar shores of our planet to uncover waves that ripple not just through water, but through space, time, and even the fabric of reality itself. From ancient Martian oceans to the icy seas hidden beneath the surface of alien moons, from supernova shockwaves to gravitational tremors born in black hole collisions, the cosmos is filled with movements as violent and mysterious as any wave on Earth. These cosmic tsunamis are not merely metaphors. They are real, measurable, and often terrifying in their scale. They shape planets, erase atmospheres, and reveal the deep interconnectedness of all things, from the smallest particle to the largest galaxy cluster. In exploring these waves, we may come to understand something profound, that the universe itself behaves like an ocean, and we, adrift on a fragile world, are passengers riding the ripples of a much grander sea. "66 million years ago, the Earth was teeming with life. Towering dinosaurs roamed lush valleys, while vast oceans shimmered under the sun. But above this vibrant world, something ancient and cold was falling. A space rock, larger than Mount Everest, descended toward the Yucatan Peninsula. When it struck, the explosion unleashed energy that dwarfed every volcano and earthquake in history. Firestorms swept the skies, shockwaves fractured the crust, and then came the waves, impossibly tall walls of water rising from the sea like a planetary scream. The asteroid's impact into the shallow ocean did not merely disturb the water. It hurled billions of tons of seawater skyward. The ocean recoiled, then surged outward in all directions. Tsunamis, unlike anything Earth had ever seen, began their deadly march. Near the impact site, the waves stood more than 1,000 meters tall. Entire coastlines were erased. Forests were stripped bare. In mere hours, the world changed. The age of reptiles ended not just with fire from the sky, but with water from the deep. The sea, usually a cradle of life, became an instrument of extinction. The mechanics behind such waves are as terrifying as they are simple. When an asteroid plunges into the ocean at tens of kilometers per second, it deposits its kinetic energy instantly into the water. This violent release pushes millions of cubic meters outward, sending a shock through the sea that becomes a tsunami. Unlike earthquakes, which transfer energy from shifting plates below, asteroid impacts strike from above, displacing the surface with raw, sudden force. The ocean has no time to react gently. It simply explodes outward. In deep water, these waves may appear as fast-moving humps, barely noticeable. But they travel faster than a commercial airplane, and as they reach continental shelves, they rise sharply. Coastal cities do not see a curling wave. They see a massive wall, often with multiple crests, smashing forward with relentless momentum. Modern simulations of the Chicxulub impact show that these waves may have crossed entire ocean basins. The Pacific, Atlantic, and Indian Oceans all carried the echoes of that violent hour. The planet itself rang like a bell. Asteroid-generated tsunamis differ profoundly from those caused by tectonic activity. Earthquakes begin below the sea floor, and although their tremors can be severe, they often offer some warning, minutes, sometimes hours. A network of seismic sensors may detect their ripples before the wave reaches shore. But with an asteroid, there is no forewarning. There is no tremor. There is only sudden impact, a blinding flash, and then a wall of water racing outward faster than a jetliner. Moreover, tsunamis from space do not always follow a single predictable path. Their force is often asymmetrical, shaped by the angle of impact, the depth of the ocean, and even the coastline's geography. Multiple shock waves may generate overlapping waves with chaotic intervals and unexpected timing. A second or third wave may strike long after the first has receded, catching survivors unaware. The violence of the sea, amplified by a visitor from space, becomes impossible to model perfectly. And therein lies the danger. It is not just powerful, it is unpredictable. What makes these cosmic waves even more terrifying is their global reach. A meteor impact in one hemisphere can send destruction to the other. Unlike storms or tectonic shifts, which are often local or regional, an asteroid's wrath is planetary. The dinosaurs learned this lesson at the cost of their existence. For us, it remains a question of time. The sky above is not empty. It is full of ancient stones waiting for their moment to fall, and when they do, the sea will rise once again. Above our heads, unseen by most and unfeeling in their silence, thousands of rocky bodies orbit the sun. These are the near-Earth objects, or NEOs, asteroids and comets, whose paths intersect or approach our planet's own. NASA and other space agencies monitor more than 25,000 of them, each with its own trajectory, size, and potential threat. Some are no wider than a school bus. Others are as large as a mountain. These are not science fiction villains. They are real, ancient remnants of the solar system, and they are watching us as we watch them. The unsettling truth is that not all of them have been discovered. Many NEOs are dark, non-reflective, and move unpredictably through the vast canvas of space. Some may appear only weeks before a close approach. Others may remain invisible until it is far too late. Every few decades, a meteor like the one over Chelyabinsk, Russia, reminds us how quickly the sky can come alive with violence. That object was just 20 meters across, and it still injured over 1,000 people with nothing more than a shock wave. What if it had been 2 kilometers wide? What if it had struck the ocean? In 2022, humanity made history. The DART mission deliberately crashed a spacecraft into an asteroid to test whether its orbit could be changed. And it worked. For the first time, we proved that planetary defense is not just theory. It is possible. But changing an asteroid's path requires time. If we discover an object only days before impact, the best technology will be useless. There will be no time to deflect. The only option would be evacuation. But evacuation is not so simple. Consider a major city like Jakarta, Mumbai, or Tokyo. Imagine trying to move millions of people away from a coastline in less than 72 hours, with global panic spreading faster than the wave itself. Roads would clog, resources would run dry. In the confusion, misinformation would thrive. Fear would ripple across borders, just like the wave that follows. The challenge is not just physical, it is psychological. Humans are not wired to respond to cosmic threats until they are far too close. Planning for such an event requires imagination, coordination, and trust, qualities that are often in short supply. While satellites scan the sky and supercomputers model trajectories, the question remains: will we act when the warning comes, or will disbelief and delay become our downfall? In the age of data, the hardest thing may not be predicting the danger, but believing it when it arrives. Today, the sky appears peaceful. Stars blink overhead. The moon drifts silently through its phases. But this calm is an illusion. The universe is in motion, and its debris travels with it. We live in a brief moment of quiet between impacts. The last great wave struck 66 million years ago. The next could arrive tomorrow, or not for 100 centuries. The timing is uncertain. The risk is not. When it comes, it will not sound like thunder. It will come as light, then fire, then sea. A wall of water racing across the globe. A wave older than history, shaped by a force beyond control. The only question is whether we will be ready, not just with rockets or sirens, but with the humility to accept that in the theater of the universe, we are not the ones writing the script. We are passengers, and sometimes the tide will rise. At first glance, Mars appears barren and dead, a dusty world of red sand, broken rocks, and frozen silence. But across its northern hemisphere lies a vast plain called Vastitas Borealis. It is flat, low, and oddly smooth, leading some scientists to believe it once held a massive ocean. If true, this Martian sea would have covered 1/3 of the planet's surface. But if there was an ocean, where are the beaches? Where are the ancient shorelines carved by waves, etched by tides, or layered by sediments? For years, this question puzzled planetary scientists. On Earth, oceans leave scars that last millions of years. Coastal cliffs, sandy terraces, estuaries. Yet, on Mars, the boundaries of this ancient sea were strangely absent. Early satellite images showed only faint hints of shoreline, interrupted by impact craters and lava flows. It seemed as though something had erased the edges, or perhaps something had buried them. The lack of clear coastal features led some to doubt the ocean theory entirely, until new evidence emerged. In 2016, researchers studying Martian topography identified something unexpected: vast chaotic terrains that looked eerily familiar. They resembled the aftermath of tsunamis on Earth: sloping ridges, jumbled debris, and inland deposits that did not match wind erosion or glacial movement. These features, scientists proposed, were left behind by massive waves that once surged inland across Mars's northern plains. But what could have caused them? The answer pointed skyward. Two enormous impact craters, named Lomonosov and another unnamed structure, matched the age and location of these disturbed regions. Researchers suggested that asteroid strikes into the Martian ocean triggered mega-tsunamis. These waves would have been at least 70 meters tall, reaching hundreds of kilometers inland. In some areas, the waves appear to have wrapped around elevated plateaus, climbed into valleys, and then drained back into the ocean basin. The scars they left behind are still visible today, frozen in time and dust. To understand the scale of these Martian tsunamis, scientists turned to simulations. Imagine an asteroid the size of a city plunging into a shallow sea. The energy released would instantly displace billions of tons of water, sending shockwaves through the ocean. Within minutes, waves higher than a 5-story building would radiate outward, unhindered by vegetation, atmosphere, or tides. Mars, being smaller and colder than Earth, would freeze many of these waves in place shortly after they struck land. Unlike Earth, where erosion and weather erase ancient landscapes, Mars preserves them. The waves from these impact-induced tsunamis did not just flood the land, they reshaped it. They pushed boulders the size of houses. They carved paths into the Martian soil. And then, as the water receded, they left behind lumpy, chaotic deposits with no clear source. These frozen fingerprints have become some of the strongest clues that Mars once had a dynamic, violent ocean. Some of these simulated waves traveled more than 400 kilometers inland. In certain regions, you can trace the direction of flow from crater to deposit, like following the trail of a vanished river. The tsunamis might have erased earlier shorelines, covering them in mud, rocks, and frozen brine. Ironically, the reason we could not find the coast of the Martian Sea may be because it was swept away by the sea itself. In trying to solve one mystery, we stumbled upon an even deeper one that reaches not only into the past, but perhaps into the nature of life itself. After the tsunami waves crashed onto the Martian plains and rushed back toward the ocean basin, they did not simply vanish. Instead, they left behind something haunting: In several low-lying regions, scientists have discovered clusters of circular depressions, shallow basins that contain chemical signatures of salt and ancient ice. These formations are not typical impact craters. Their shape, composition, and location suggest they were once temporary lakes, formed by water, trapped after the waves withdrew. And then, as the Martian atmosphere could not sustain liquid water, they froze. These frozen basins became ghost lakes, remnants of a flood no one witnessed, sealed by time and cold. Within them, researchers have found deposits of chloride salts, similar to those found in Earth's dried lake beds. On Earth, such environments can preserve organic matter for millions of years. If life once existed in the Martian ocean, these circular basins could be the places where it was last protected, entombed in ice and salt, waiting beneath the dust. They are both graveyards and time capsules, and perhaps the closest Mars has to memory. If Mars once had an ocean, then it may have also had life. The presence of liquid water, salts, and heat from impacts creates a recipe known to support microorganisms on Earth. In this light, Martian tsunamis take on a deeper meaning. They were not just geologic events, but biological ones. These waves may have destroyed, yes, but they may also have delivered. Microbes from deep in the sea could have been thrown inland, embedded in mud and ice, and preserved by the same cold that ended the water's flow. It is a haunting possibility. Imagine extremophiles, tiny, resilient organisms flung across the Martian landscape, some dying, others frozen in place. Like seeds scattered before winter, they wait for spring that may never come. Perhaps some found refuge in the warm aftermath of the impact zones, where hydrothermal activity could have continued for decades. Or perhaps their genetic traces still sleep beneath the scarred surface, waiting for us to drill deep enough, to look closely enough, to ask the right question at the right depth. The evidence for tsunamis on Mars is compelling. It tells a story of oceans, impacts, flooding, and freezing. A saga written not in words, but in the shape of land and the chemistry of soil. It reminds us that Mars was not always dead and silent. It had energy, chaos, and motion. It had seas that rose and collapsed. It had moments of violence that reshaped its face. And if that much can be true, then so might the next step, that somewhere in that ancient water, something once lived. Yet for all we now suspect, one truth remains clear. We have only scratched the surface. Mars hides its past beneath dust and ice, and only with patience, precision, and imagination can we uncover its deeper secrets. Each rock we turn, each crater we map, each sample we study may hold a clue to the grander story, not just of Mars, but of life itself. In the silence of a world long dried, the waves still echo. Perhaps one day, when humans walk these plains, they will stand on the edge of one of those frozen circles, brush away the dust, and find not just water, but memory. the memory of a world that once moved like our own, the memory of a wave that may have carried life, the memory of a sea that is gone, but not forgotten. Far beyond the asteroid belt, orbiting the gas giant Jupiter, there is a world that seems quiet and still. From space, Europa appears like a smooth, icy marble, etched with reddish-brown cracks that stretch across its surface. But beneath this calm exterior lies one of the most mysterious and promising places in the solar system. Scientists believe that under Europa's frozen shell exists a vast, global ocean. It is not a lake, not a pocket, but a sea larger and deeper than all of Earth's oceans combined. Europa's ocean may be buried under 10 to 20 kilometers of solid ice, yet its depth could reach over 100 kilometers. That means it holds more than twice the amount of liquid water found on Earth. This is not speculation. It is grounded in decades of data from spacecraft flybys and magnetic readings. If there is one place beyond Earth where water flows freely in the dark, where heat meets salt, and where chemistry becomes possibility, it is here, beneath the ice of Europa. Though sealed from space by a crust of ice, Europa's ocean is not likely still. The surface is covered in fractures, ridges, and chaotic terrain, signs that the ice is being flexed, cracked, and shifted from below. These features are shaped by tidal forces from Jupiter, which constantly stretch and compress Europa as it orbits the massive planet. This flexing generates heat, enough to keep the subsurface ocean from freezing solid, and enough to cause the icy shell to groan and move. Some regions show signs of resurfacing, where older ice appears to have broken apart and been replaced by newer, cleaner material. These areas suggest that water from below may have pushed upward, flooding and refreezing, or perhaps erupting in geysers that sprayed into space. Observations from the Galileo spacecraft and later the Hubble Space Telescope have hinted at such plumes. If true, they would mean that Europa is not only active, it is dynamic, with water communicating through cracks and fissures. If Europa's ocean is indeed alive with motion, it raises an extraordinary question. Could there be tsunamis beneath the ice? While there is no wind, no tectonic plates like on Earth, the forces at play are immense. A sudden shift in the ice shell, a quake triggered by tidal stress, or even a small asteroid impact could displace water on a massive scale. Without an open sky to release energy, that force would remain trapped, bouncing between the ocean floor and the underside of the ice. Simulations suggest that such sub-ice tsunamis could create pressure waves capable of cracking the surface, forcing jets of water upward, or redistributing minerals and heat. These waves would not be visible from space, but their consequences might be. Jagged ridges, chaotic terrain, and irregular thermal signatures could all be scars of ancient underwater upheaval. Like silent avalanches in the dark, these hidden tsunamis could be reshaping Europa from within. The possibility of tsunamis under Europa's ice is more than a dramatic idea. It may be a crucial key to understanding the habitability of this distant moon. Such waves could stir nutrients, carry heat, and mix chemical ingredients in ways essential for life. If life ever emerged there, or still survives, these deep, hidden tsunamis may be part of the system that sustains it. In Europa's cold ocean, motion may be life's first language, and waves its oldest whisper. On Earth, life thrives not only in sunlight, but also in the darkness of the deep ocean. At hydrothermal vents, thousands of meters below the surface, heat and chemistry sustain entire ecosystems. No light required. Europa may offer a similar story. Beneath its icy shell, energy from tidal heating and chemical reactions could create habitable zones. And if underwater waves exist there, driven by quakes, impacts, or shifting ice, they could help stir that ocean, mixing nutrients and distributing heat, much like currents in our own seas. In such a setting, even a small motion could matter. Subsurface tsunamis might drive materials from the seafloor into the upper layers, where they interact with oxidants that seep through the ice. This chemical dance could support metabolism, the foundation of all known life. Waves may also circulate warmth, preventing the ocean from stratifying into lifeless zones. In this sense, Europa's hidden tides and waves are not just physical forces. They are lifelines, silent, invisible mechanisms that could make life not just possible, but sustainable. For decades, Europa has been a world of speculation, but soon it will become a world of data. NASA's upcoming mission, Europa Clipper, is set to launch in the coming years and will arrive in the Jupiter system later this decade. Its goal, to perform dozens of close flybys of Europa using radar, spectrometers, cameras, and magnetometers to peer beneath the ice, study the surface, and look for signs of habitability. It will not land, but it will listen. It will measure. It will ask questions no machine has asked of Europa before. One of the most exciting instruments aboard the Clipper is an ice-penetrating radar. It will send pulses through the frozen crust, mapping the structure of the ice and possibly identifying pockets of liquid water or regions of recent movement. If the mission detects irregularities, such as thin spots, thermal anomalies, or evidence of recent upwelling, it could confirm that Europa is not only geologically active, but hydrologically alive. The mission may not find life, but it could bring us one step closer to knowing where life might be. Imagine a place where no sunlight has ever touched the water. A sea buried under ice, cloaked in eternal night, where the only energy comes from within. In that vast and silent deep, it is not hard to imagine microscopic organisms drifting slowly through the currents, single-celled life clinging to chemical gradients, adapting to the push and pull of underwater tides. If Europa harbors life, it may not be dramatic or intelligent. It may be ancient, simple, and quietly enduring. But it would change everything. To find life on Europa would be to prove that biology is not unique to Earth. It would mean that life can emerge in darkness, survive without the sun, and perhaps be common wherever there is water and energy. That knowledge would ripple across our understanding of the universe. It would reshape how we see our own planet. It would whisper that we are not alone, that life is not a miracle, but a pattern. And so we wait, watching this icy moon from afar, listening for signs from below the surface. One day, perhaps soon, we will know what moves beneath the frozen skin of Europa. And if we find nothing, the silence will still speak volumes. For in that frozen silence, we may yet hear echoes of waves, and in those waves, the stirring of life. The outer solar system is not just a realm of gas giants and icy emptiness. It is also home to a surprising number of small, frozen moons, worlds that may be far more dynamic than they appear. Around Jupiter and Saturn orbit dozens of satellites, many of them once dismissed as barren rocks. But beneath their icy crusts, scientists now suspect that several of these moons hide deep oceans of liquid water. They are Europa, Enceladus, Titan, Ganymede, and more. A hidden family of ocean worlds, each with its own story, its own tides, and possibly its own version of life. In some ways, the moons of Jupiter and Saturn form a miniature solar system of their own. Each one interacts with its host planet and with its siblings through gravity, radiation, and heat. The result is a set of unique environments where water is common, chemistry is active, and energy is plentiful. What is remarkable is not just that these oceans exist, but that they may be moving. Waves, currents, and perhaps even tsunamis might be stirring in these buried seas, shaping not only the geology of these moons, but also their potential for life. Among these distant worlds, few are as captivating as Enceladus, a small moon of Saturn no wider than the state of Arizona. At first glance, it seems cold and lifeless. But in 2005, the Cassini spacecraft discovered something extraordinary. From deep fractures near its south pole, Enceladus was spraying towering plumes of water vapor and ice grains into space. These jets came from beneath the surface, from a salty ocean sealed under a shell of ice. The moon was not just geologically active, it was breathing. Cassini flew through the plumes and analyzed their contents. The findings were astonishing. The vapor contained water, salts, methane, ammonia, and complex organic molecules, the building blocks of life. Even more surprising, the data suggested that the ocean was in contact with a rocky core, meaning that hydrothermal activity could be occurring on the sea floor. On Earth, similar environments teem with life. On Enceladus, they could be doing the same. But how does this hidden ocean stay alive? What forces drive it? One emerging idea is that Enceladus may be experiencing internal waves, not waves of light or sound, but waves of pressure and motion within its buried ocean. The powerful gravitational pull of Saturn flexes the Moon as it orbits, creating tidal forces that stretch and compress its interior. This constant kneading generates heat, which keeps the water from freezing and may even trigger sudden shifts in pressure. These shifts could create waves, perhaps even tsunamis, that travel beneath the ice, stirring the ocean and shaping the surface above. Though hidden from view, these sub-ice waves might explain the rhythmic behavior of the plumes and the strange textures on Enceladus's crust. They may push water upward, crack the ice, and force plumes into space. They may circulate nutrients and minerals from the rocky bottom to the upper layers, feeding any life that might be drifting there. On a world without light, such waves would act as silent engines, spreading warmth, distributing energy, and perhaps keeping the ocean alive. If so, Enceladus is not just active, it is a moon in motion, alive with unseen tides. If there is one moon in the solar system that resembles a planet, it is Titan. Bigger than Mercury, wrapped in a thick orange atmosphere, Titan is the only moon known to have lakes, rivers, and rain on its surface. But this is no familiar water world. Titan's weather runs on methane. Its clouds form from hydrocarbon vapors. Its lakes are filled with liquid methane and ethane, and its surface is shaped by precipitation and erosion, just like Earth, but colder, darker, and stranger in every way. Beneath this alien landscape lies something even more astonishing. Radar data from the Cassini mission suggests that Titan hides a subsurface ocean of water, trapped beneath hundreds of kilometers of ice. This ocean could be global and may be interacting with the rocky core below. While the methane seas above shift with the seasons, the water below may move in deeper, slower waves. Some scientists believe pressure changes from within Titan's crust could produce internal quakes, possibly even slow, muffled tsunamis beneath the surface. Titan and Enceladus are not alone. Other moons in the solar system also show signs of buried oceans. Ganymede, the largest moon of Jupiter, and the largest moon in the entire solar system, likely contains a layered ocean beneath its icy shell. Its surface shows grooves and ridges, hinting at past tectonic activity. Callisto, another Jovian moon, may also hold an underground sea, though one that is older, colder, and less dynamic. These worlds may not erupt like Enceladus, but their quiet stillness does not rule out motion below. Farther out, orbiting Neptune, Triton offers one of the most mysterious cases. It is a captured object, likely once a dwarf planet, now spiraling slowly toward its host. Triton has geysers of nitrogen ice, a retrograde orbit, and a surface marked by cracks and frozen plains. Some models suggest that it too could harbor a subsurface ocean, warmed by radioactive decay. If so, it would be a world of distant, silent tides, an echo of warmth in a realm of deep cold, where the idea of waves feels more like memory than motion. Across the solar system, beneath layers of ice and clouds, There may be oceans that breathe, shift, and stir. Some are calm, others erupt. Some lie beneath methane skies, others under frozen silence. But what unites them is the possibility of motion, of waves that roll unseen in the dark. These are not the waves we know from Earth's shores. They are deeper, slower, and older. Yet they may carry with them the same ancient energy that gave rise to life here. In their rhythm, there may be biology. In their silence, memory. We used to believe Earth was the only ocean world. Now we know better. The cosmos is not static. It pulses with tides we are only beginning to feel. In Europa, in Enceladus, in Titan, even in distant Triton, the universe reminds us that where there is water, there is movement. And where there is movement, life may not be far behind. Perhaps, in the end, the universe is not a vast emptiness. It is a sea of hidden waves, and we are just starting to listen. We often think of light as life-giving, as something warm, gentle, and essential. But not all light is kind. In the vast reaches of space, there are events so powerful that light itself becomes a weapon. A supernova, the death explosion of a massive star, is not just a dazzling burst of brilliance. It is a tidal wave of radiation, a flood of high-energy photons that can sweep across space at the speed of light. And if such an event happens close enough, it does not need to strike a planet directly. The light alone can destroy everything. Imagine a star dying in a distant corner of the galaxy. Within seconds, its collapsing core triggers a chain reaction that tears it apart. The explosion is visible across millions of light years. But more than that, it sends out a wave of radiation so intense that it can disrupt the atmospheres of planets far away. This is not a gentle sunset or a beam of sunlight through trees. This is a wall of energy, a cosmic tsunami made of photons and particles, capable of erasing ecosystems without ever touching the surface. At the heart of every supernova is a dying star that has exhausted its fuel. Without the pressure from fusion to support its immense gravity, the core collapses inward. In a fraction of a second, matter is crushed into an ultra-dense state, triggering a rebound effect so violent it rips the star apart. This rebound sends out shock waves, light, neutrinos, and a storm of radiation in every direction. The explosion is not just bright, it is ferocious. The energy released in a typical supernova equals what our sun will emit over its entire 10 billion-year lifetime, all unleashed in just a few moments. This wave of radiation expands outward through space, lighting up nebulae, seeding new stars, but also endangering any planet in its path. The leading edge of this wavefront is made of ultraviolet rays, X-rays, and gamma radiation. Forms of light invisible to the eye, but deadly to life as we know it. It is a silent, blinding flood that brings extinction, not enlightenment. If a supernova occurred within 50 to 100 light-years of Earth, we might never see it coming. The flash would reach us in a burst, silent, sudden, and merciless. One of the first effects would be the erosion of our planet's ozone layer. Without this protective shield, Earth would be exposed to intense ultraviolet radiation from the sun. This could lead to mass extinctions, starting with the delicate web of oceanic plankton that supports the marine food chain. Some scientists believe that past extinction events on Earth may have been caused or worsened by nearby supernovae. Radioactive isotopes found in ancient ocean sediments suggest that such explosions may have bathed our planet in waves of energy long before humans walked the Earth. These events do not leave craters, but their fingerprints remain in the layers of rock, in the fossils that vanish suddenly, and in the invisible scars of disrupted DNA. It is a reminder that even light, in the wrong form, can unmake a world. Among the deadliest phenomena in the cosmos are gamma-ray bursts, short-lived but unimaginably powerful explosions of pure energy. These events occur when two neutron stars collide or when a supermassive star collapses into a black hole. In just a few seconds, a gamma-ray burst can release more energy than our sun will emit over its entire life. But unlike a supernova, this energy is not dispersed equally in all directions. It is focused into a narrow beam, a concentrated jet of annihilation that travels at nearly the speed of light. If that beam were aimed directly at Earth, it could sterilize the planet. It would destroy the ozone layer, ignite atmospheric reactions, and cause a mass extinction within moments. Thankfully, gamma-ray bursts are rare and usually point away from us, but their sheer potential for destruction reminds us how vulnerable we truly are. These are not just flashes of light, they are cosmic scalpels, cutting through space with terrifying precision. They are the tsunamis of energy that do not crash. They slice and they erase. What makes these cosmic threats so unsettling is that they require no physical contact. On Earth, a disaster usually involves impact, an earthquake, a hurricane, a falling asteroid. But in space, the rules are different. A planet can be destroyed by light alone. Photons, though massless, carry momentum, and when they arrive in concentrated streams of radiation, they can rip molecules apart, shred atmospheres, and trigger chemical chaos on worlds they never even touch. This means that a habitable planet, orbiting peacefully around its star, can be sterilized by an event occurring dozens or even hundreds of light years away. No collision, no warning, just a sudden burst of light from the darkness. It is a reminder that the fabric of space is not just distance and silence. It is tension, pressure, and potential, waiting to be unleashed. The universe is not empty. It is active, and sometimes it is lethal. We often speak of light as a metaphor for knowledge, hope, and life. But in these extreme corners of the universe, light turns on us. It becomes the destroyer. The same photons that power photosynthesis and warm our skin can, in other forms, strip atmospheres bare and reduce thriving ecosystems to ash. There is a strange poetry in that. The very thing that allows life to exist can also be the thing that ends it. In the heart of every supernova and at the tip of every gamma-ray burst, light becomes a force of extinction. And yet, this destructive light also seeds the galaxy with heavy elements: iron, gold, uranium, things forged in fire and scattered by wave. Without that light, we would not exist. We are children of stellar violence, made from the ashes of stars and the echoes of waves that once swept through space. Light kills, but light also creates. That is the paradox at the heart of the cosmos, and the story it continues to tell. Imagine space not as a void, but as a surface, smooth, silent, undisturbed. Now imagine something massive, like two black holes, colliding in that stillness. The impact would not throw debris or fire. It would ripple the surface itself. Gravitational waves are those ripples, disturbances that move through the fabric of space-time, stretching and compressing it as they go. They are not made of light or matter. They are made of space itself, in motion. In a universe that often hides its violence, gravitational waves are the tremors left behind by titanic events. They are not waves in the air or water. They do not shimmer or glow. Instead, they quietly expand and contract the space between objects. If a gravitational wave were to pass through your body right now, it would stretch you lengthwise and squash you sideways, by a distance smaller than an atomic nucleus. You would never feel it. But the universe would have changed, ever so slightly. And those changes, though small, carry the memory of cosmic collisions from across the galaxies. More than a century ago, Albert Einstein imagined that space and time were not separate, but woven together into a single fabric, space-time. And in this fabric, gravity was not a force pulling objects together. It was the curvature of space caused by mass. In 1916, Einstein predicted that when massive objects accelerated, they would send ripples through this fabric, gravitational waves. It was a beautiful idea, elegant and bold. But there was a problem. The waves were so faint that many believed they could never be detected. For decades, gravitational waves remained a theoretical whisper, hidden beneath the noise of the universe. Telescopes saw stars and galaxies. Radios heard pulses from quasars. But no one could hear the ringing of space-time itself. It was not until the 21st century that the tools became sensitive enough. In 2015, scientists at the Laser Interferometer Gravitational Wave Observatory, LIGO, detected the signal from two black holes colliding more than 1 billion light-years away. Einstein's whisper had become a sound. When two massive bodies, like black holes or neutron stars, spiral toward each other, they stir the space around them. Their movement distorts the space-time fabric, generating waves that propagate outward at the speed of light. These waves stretch and compress everything they pass through, though only by the smallest of margins. Gravitational wave detectors like LIGO work by using lasers to measure these minute changes in length, detecting movements far smaller than a single proton. It is like listening for an earthquake in the structure of the universe itself. These waves do not fade easily. They travel for billions of years, unimpeded by gas, dust, or light. When they finally reach us, they tell the story of what caused them, how big the objects were, how fast they moved, and how violent their collision was. In essence, gravitational waves are not just echoes of the past. They are messages written in the geometry of space itself, and we have only just begun to read them. For centuries, astronomy relied entirely on light. Telescopes captured it, spectrometers analyzed it, and every distant star or galaxy we studied spoke to us through the electromagnetic spectrum. But light has limits. Some events in the universe are shrouded in darkness. Black holes do not emit light. The moments before the Big Bang left no photons behind. In these blind spots, gravitational waves offer something revolutionary, a way to see the invisible, not by detecting what glows, but by feeling what shifts. These waves allow us to observe cosmic collisions that would otherwise be silent. When two black holes merge, they do not shine, but they roar in gravitational waves. These waves carry unfiltered information, not distorted by gas clouds, not dimmed by distance. They offer a direct link to the most energetic, most violent moments in the cosmos. Through them, we are not just seeing the universe, we are listening to it. We are touching the ripples left behind by events that unfolded billions of years ago. Unlike light, gravitational waves are not stopped by walls of matter. They do not scatter or bounce. They move through stars, planets, and even your own body without resistance. In that sense, they resemble a tsunami, not made of water, but of space itself. When they pass, everything momentarily stretches and compresses. The Earth swells ever so slightly. Atomic distances shift, but the wave leaves no damage, no trace. Only the whisper of movement, captured by machines of impossible precision. They are silent, but they are immense. Their power is not in destruction, but in information. Gravitational waves carry the shape of the dance that made them, the final spirals of black holes, the collapsing cores of dying stars. Each wave is a fingerprint, etched into the geometry of the universe. And though they are faint by the time they reach us, they still speak clearly to those who know how to listen. In their stillness, they carry the weight of ancient violence and the promise of deeper understanding. Gravitational waves challenge us to rethink what space really is. No longer just a background for stars and planets to drift through, space becomes an active medium, a sea that can ripple, heave, and tremble. In the presence of immense gravity, space does not remain still. It reacts, it responds, it moves. And in doing so, it records the memory of cosmic events, like waves in a pond remembering the stone that disturbed them long after it has sunk. We are only beginning to explore this hidden ocean. What else might we learn from waves not yet detected? From disturbances we do not yet recognize? Just as sound once opened a new way of understanding Earth's interior, gravitational waves are opening the deep interior of the cosmos. In this sea of space-time, we are not merely observers, we are passengers, floating on a surface that is always, quietly, in motion. In our search for exoplanets, we have discovered something remarkable. Among the thousands of worlds orbiting distant stars, some appear to be completely covered in water. Planets with no land, no continents, only endless ocean. These so-called ocean worlds, like Kepler 22b or GJ 1214b, challenge everything we thought we knew about planetary formation. They are deep, alien seas under unfamiliar skies, and where there is ocean, there is the potential for waves. Tsunamis on these distant worlds would not be like those on Earth. With stronger gravity, thicker atmospheres, or even subsurface oceans beneath exotic ice layers, the mechanics of wave formation would be dramatically different. Yet, the principles remain. A meteor strike, a tectonic shift, or a gravitational tug from a nearby moon could still create waves that ripple across the planet's entire surface. And in the absence of land, there would be no coast to stop them, only water, rolling endlessly into water. When we step back far enough, something becomes clear. Waves are everywhere. They carry energy, momentum, and information. In oceans, in air, in light, in gravity, every fundamental force seems to ripple. The universe does not speak in words, it speaks in waves. From the trembling of atoms to the spiraling of galaxies, everything oscillates, everything pulses. Waves are the patterns etched into the fabric of existence, and perhaps they are its most ancient language. Even time may not flow evenly, but rhythmically. Even space may not be still, but breathing in slow, immeasurable beats. Waves unite the smallest and the largest. They carry photons from distant stars, bring sound through air, and echo through space-time itself. To understand the universe is to understand its waves, to listen closely to the ripples, the pulses, the tremors. Not all waves are violent. Some are subtle. Some are constant. But all of them speak, and we are only beginning to listen. Perhaps the ultimate truth is this: the universe is not built like a machine, with rigid parts and fixed paths. It is more like a sea, deep, mysterious, in motion. And in that sea, waves are not just disturbances. They are messages. They are memories. They are the music of the cosmos. And we, afloat on our tiny planet, are beginning to hear the harmony that has been playing since the beginning of time. From waves crashing upon our earthly shores to ripples that stretch across the very fabric of space-time, this journey has shown us that motion, vibration, and upheaval are not limited to oceans alone. The universe is not a silent void. It pulses, surges, and trembles with unseen waves. Some carry light across billions of light years. Others shake the cosmos with the last breath of dying stars, and some, perhaps, still wait to be discovered. In all of them, there is a pattern, a rhythm, a whisper that says everything is connected. We often think of ourselves as solid, separate beings, fixed points in a grand design. But in truth, we are part of the wave. Our atoms vibrate, our hearts beat, our thoughts move like tides. On the largest scales, galaxies swirl in currents drawn by gravity. On the smallest scales, particles flicker and interfere like ripples in a quantum pond. The distinction between us and the cosmos begins to blur when we see ourselves not as observers of waves, but as participants within them. Perhaps that is the most humbling lesson of all. We are not outside the universe looking in. We are not immune to its storms or detached from its tides. We are waves within waves, patterns within patterns, a brief shimmering on the surface of something far greater. And just as a single ripple in an ocean can travel across worlds, our existence, fleeting as it may seem, becomes part of the universe's eternal motion. In the end, we are not separate from the cosmic sea. We are the sea, aware of itself. If you enjoyed this video, please give it a like and subscribe to our channel. Let us know your thoughts in the comments. We'd love to hear from you. Thanks for watching, and we'll see you in the next one.